And this is 4-4 alpha lesson. So we're going to start at the end. And the end is this problem from the back, problem 56. And they give you this picture. Now, this isn't like the real world problems, but that are in the section. But it's a question that you're using calculus to solve. So you have this rectangle that's inscribed between these two parameters. Y equals 4x squared and y equals 30 plus a negative x squared, as shown. Except the rectangle doesn't have to look like that. The rectangle could look like this. Right? The rectangle could be taller, it could be wider, it could be, but it's inside these two parameters. And you want to find the maximum area of that rectangle. So think about what you do have to do for the quiz tomorrow, and think how that relates to how you would maximize the area of that rectangle, right? So we're going to come back to this problem, but we're showing it to you ahead of time and say, imagine if you were asked to do this, for example, an exit ticket. It's a pretty user-friendly question. After we've done the section, right now, it looks like it's majorly kept. So in the book, we're going to start with example 1, which says, find two numbers whose sum is 20 and whose product is as large as possible. Does that make sense? So you need two numbers that are up to 20. So if one of them is an unknown, we would identify it by a variable, yes? So you say, okay, the first number is x. And you have to add something to x, so you end up with 20. Because the two numbers have to add up to 20. So what do you add to x to give you 20? Very good. Erzberg, you have to introduce the number and you have to eliminate the variable. So you would add 20 plus a negative x. And then the x's would add to 0, and you'd have a 20 as the sum. Is that logical? These two numbers add to 20. And what do you want to do? You want to have the maximum product possible. The product would be x times 20 plus a negative x. Call that P for the product. So P equals 20x plus a negative x squared. We want the maximum area. Does that make sense? So what do you think of doing? What's on the quiz? I'm not pausing the video right here. This is just science. What would the approach be under the circumstances? Yeah. Yeah, exactly right. What have you been doing for 3 months? You take the derivative of P with respect to x. So P equals that. dP dx would equal 20 take away 2x. Now what? Set it equal to 0. That's what we've been doing. And identify the SIGN change. So if we do that, our H chart looks like this. If we set this thing equal to 0, we add a negative 20 to both sides. Divide both sides by a negative 2, you would get 10. 10 makes the derivative 0. You have to confirm the sign change. I don't know, put 9 in there. 20 subtract 2 times 9 is 18, it's positive. Put 11 in there. 20 subtract 2 times 11 is negative. what happened? You have a sign change. The derivative goes from positive to negative, which means the parent graph was going from increasing to decreasing. You wanted the maximum product of those two numbers, so that would occur at 10, which is exactly what's on the quiz, except it was in the context of this word problem. Example 2. There's a picture in the book on page 219 on the left, and it says, you want to put this rectangle inscribed under one arch of the sine curve. So this is like the question at the end. You have this rectangle which they drew. This made up these values P and Q, meaning P and Q could be here. There's a rectangle. That's not the answer in the picture in the book. That's a rectangle. P and Q could be here. It could be that rectangle. But what you're trying to do is say, this rectangle is inscribed in the sine wave, and it's maximizing the area. So what's the approach? Well, first thing you have to understand is this. Just like we started the first problem about the product, we have to introduce a variable. So it makes sense, I think, to say, okay, pretend this is the origin. How far to the right, what is the input for point P? I don't know, I'm traveling horizontally, let's call it X. What's the height of P? So I will pause the video for a second. If you go X units to the right, this would be the point. X, comma, what? Why does it help you? Because you can't have two variables. So think in context of the question. What is y equal to? That's the same thing. It's a synonym for what? What is it in context of the question? How tall is that rectangle? Sine x. It's not complicated. It's written right down in front of you. If you go, oh, I just gotta, ready? X to the right, up, sine x. Because this point is hitting the curve. Yes? What's this point? Well, this is an effect, ready? 0 plus x. As we said, start at the origin, you go x units to the right. So then this magnitude would be x. So how can you describe that input? It's x units to the left of what? Pi, thank you, why? Because that's when the sine wave is going to hit the x-axis again. So this would be pi plus a negative x. And then this height would be, ready? Pi plus a negative x, comma, sine of pi plus a negative x. And then what? Well, the magnitude of my rectangle would be, right take away left would be the base. Height take away, upper take away lower would be the height. You would multiply them together. That would be the area. Then we would do the same thing we did in the first problem. We have the area, so we differentiate it, looking for when the derivative is 0, a critical point, and then verifying the sign change. It was the greatest value we could have there for x. Where should we move this rectangle? Except there's a problem here. Because look what I did. I said P is x to the right, sine x. Okay, that's good. And I said Q is x take away pi, sine x. The y values. Well, because I put it based on the input. Except, stores, you are correct. They have to have the same height. So instead of calling this sine of pi take away x, we can call it sine x, because they are the same. Right? If you think in terms of the circle, pretty good. You know what they say about people who can draw perfect circles? Careful. I didn't say it. Oh, man. Here's the circle. I think this is what Stores is saying to you. Here's our x. In this case, I'm going x to the right. The magnitude of the angle. Yes. So this would be x. This would be cosine x. Sine. Right here. But there's your x. Make sense? X is the angle. So the coordinates on the circle will be cosine x sine. Then we go over here. This angle right here would be start at pi and go x in the negative direction, which is clockwise. Except, here's what Stores is telling you. The heights are the same. So sine x has the same height as sine pi take away x. So over here we wrote it as the heights are the same. This far to the right, that far to the right for the other. So what's the base of this thing? You subtract, right take away left. And the base of that picture would be this take away this, pi take away 2x. What's the height? Sine x take away 0. So the area is the base times the height. And from here to here, we distributed sine over both sides of that subtraction sign. Now what? From here to here, we took the derivative. Now you got to be careful. If pi is a constant, derivative sine is negative cosine. I'm sorry, derivative sine is cosine. So you have pi times cosine. Subtract. Product rule in here. The derivative of the first term is 2 times the second term is sine x plus 2x times derivative of sine is cosine, and you're subtracting all of that. So you end up with this messy thing here, which we did what? Which we graphed. But do you understand what we're looking for? We're looking for when the derivative, instead of building the H chart here, which you could certainly do to complement this, we look at the picture. And I'm warning you, not warning you, but recommending to you, that you look at pictures between now and tomorrow because the quiz is heavy on pictures for the first half of chapter 4. So look at this picture. This is the picture of the derivative. Ready? Here is, there's 2 critical points. This is the one we're interested in. Why? This critical point's farther to the right. Should I take the higher value? No, because I'm interested in when the derivative goes from positive to negative. Because that's telling me the parent graph, which was area, was going up. and area begins to go down. This critical point doesn't help us. Why not? The area was going down and started to go up again. So this is your local max, and that's your local min. And we're interested in when the graph has a local, when the area has a local max. So what happened? Second trace 0, and when you do that, and you go second click, it brings that value is in the cursor for X. It brings X to the home screen. So what have I got here? In Y1, I have the area curve, and in Y2, I have the derivative. So I put this 0 into Y1. So if X is ready for the AP test, we're going to truncate this to 3 decimal places. If X is 710 thousandths, then the area of the rectangle is 1 and 122,000 square units. So we will pause the video here to send you to problem 5. However, so the slope of this line segment is -1. So the parent graph is y equals -x. And you could say move it up 1, or you could say 1 to the right. You said 1 to the right, it would be y equals negative, ready? Replace x with x, take away 1. When you distribute this negative, you're going to get the same line. -x plus a +1. So the magnitude of the rectangle would be x to the right, which means your rectangle would also go x to the left. The base would be 2x. The height is your y value, 1 take away x. That's the area of the rectangle. Differentiate it, find a critical point. You set this equal to 0, x equals 1/2 is the critical point. Here's 1/2, it makes the derivative 0. So I put 4/10 and 6/10 in here. What did I get? Positive negative. The area was going up and then it started to decrease. So this is a local max. If I put this into the height, we get that. So what do you got? If this is 0.5, then the x is 0.5, then the base of the triangle is 1, because you're going 0.5 to the right, 0.5 to the left. 1 times the height of 0.5 gives you an area of 1/2 square units. You have to say, okay, you know what? This is what is on the quiz, except there's just this word problem involved. It's the same word. You have this function, and you're differentiating it, and you're setting the derivative equal to 0, and you're confirming the sign change. Because in these two problems, the example the book and the probably sent us to, we wanted to maximize this area. The next problem we're going to do minimize. So if we minimize, we find a critical point, and we want to find that the derivative is going from negative to positive. So that is example 4. So we're on page 221 at the bottom. You want to build this can, okay? You want to build this aluminum can, and you want to minimize the amount of aluminum. This is a very practical problem, okay? When you go food shopping with your mother, you should notice that no matter what aisle you're in, the packaging is the same size. Like the Coke cans are the same size as the 7-Up cans. The Campbell soup cans are the same size as another of the knockoff brand, the Giant brand soup cans. The Lucky Charms box is the same size as the Cheerios box. It's the same amount of cereal. Why? Because they're all minimizing the amount of packaging. So think of some product that has a fancy looking container. I don't know, what kind of drink do they sell at Wawa to naive teenagers? Wait a minute. What? Monster? Energy drink, yeah. And what about energy drinks? The shape of the can's different. That make sense? Because they're tall and thin. You see what they're doing? It's making you pay more money for the can. The energy drink would be cheaper if they put it in a shorter, fatter can. Teenagers don't care. Whatever looks better. First time you ever buy that energy drink. That's packaging. It's not energy. Just call them sugar drinks. Sugar and caffeine together. Throw some water in and mark it. So you got this can, ready? We want to minimize the amount of aluminum. So the dimensions of the can, you have the base, which is a circle, yes? So that'd be pi r squared. You have the lateral area, which is around the side of the can, which is the base times the height. But you have this seam here. So if you cut the can, ready? Use a can opener. Take the bottom of the can, the top off. Then you cut down on the seam of the can and you open up. What are the dimensions of the can now, the lateral area? Ready? You have the can, you took off the top and bottom. You cut it on the seam and you opened it up. What are the dimensions of that? What kind of shape is that when you open it up? It's a rectangle. And it's the height, whatever the height is, right? What would the length of that can be? Exactly, it'd be the circumference of the can. So the lateral area would be 2 pi r, which is the circumference of the can, times how tall it is. So the surface area is the lateral area plus the top and the bottom. That's the difference between surface area and lateral area. So what have we got? 2 pi r squared for the bottom of the can, pi r squared for the top of the can. It gets added to the lateral area, 2 pi r h. And what do we know? We want the volume. We don't have enough information because the problem is we got two unknowns. Area is based on R and H. No one can solve an equation with two unknowns. So we need more information. They tell you the volume of the can is meant to be 1,000 cubic units. So what's volume? The area of the base, pi r squared, times how tall it is. That's 1,000. So we got this H here, which is a headache. But we could substitute for H. What? Divide both sides by pi r squared. They would reduce. That's what H is. And if we put this where that H is, we could differentiate A with respect to R. And that's what happens in the book. Put it on my PDF. Ready? Here's their work. I'm in the middle of this page, which is 224. Here's the area, 2 pi r squared plus 2 pi r h. That's what h equals. Paste it where that h was. Now what? This r reduces with one of those r's. The pi's reduce. Distribute the 2. And you get this thing, which is 2 pi r squared plus 2,000 r to the negative 1. But you can differentiate that. You can find the derivative of a with respect to r. And this is very sloppy in the book because they rounded the value of r to 2 decimal places. It's contrary to the guidelines in the AP test, 3 decimal places. But this is what r is. The exact answer is the cubic root of 500 divided by pi. That should be the radius of your can. Because what would happen? It would minimize the surface area. Because you would be here. Your H chart would look like this. Area, the derivative area with respect to r is the cube root of 500 divided by pi. That makes the derivative 0. And a number to the left would be negative, a number to the right would be positive. So the surface area is falling till you get to that magnitude for r, and then it begins to rise. So that's the issue. You want that value to make the radius of the can for your production facility, and you will minimize the amount of packaging. If you can minimize the amount of packaging, you can minimize the cost. Or the price you charge. If the price is lower, more people will buy. So that is the alpha lesson.